welcome to the deep dive. Today, we're not talking about just, small software updates. We're looking at something much deeper, a real breakthrough in the fundamental math computers use, specifically matrix multiplication.
That's right. And matrix multiplication, well, it sounds technical, maybe a bit abstract, but it's literally everywhere. It's the engine behind the graphics in games, physics simulations, how AI models learn, even things like cryptography.
So it's running constantly behind the scenes in pretty much all the tech we use day to day.
Exactly. Rendering images, analyzing huge data sets for AI, securing online payments all rely heavily on multiplying matrices billions and billions of times. And even a tiny speed up at this core level, it can have massive downstream effects.
Which brings us neatly to AlphaEvolve. This is DeepMind's creation, and maybe think of it as a kind of Darwinian Codemaster. It's not a human team finding this. It's an AI system pushing the limits on how fast certain calculations can run.
Yeah, and the specific calculation we're focusing on is multiplying two 4x4 matrices. Now, the simple, straightforward way involves 64 individual little multiplications. Scalar multiplications.
Okay, 64. That's the baseline.
Right. Then, back in 1969, Volker-Strassen came up with a, frankly, revolutionary algorithm. Showed you could get the same answer using only 49 of those little multiplications. That was huge. It wasn't just shaving off a bit of time. It changed how we thought about the problem's complexity.
Revolutionary is definitely the word. And that 49 multiplication record, it held for 56 years?
56 years. Think about all the computing progress in that time, Moore's law, everything, and that 49 number just stood there.
Until AlphaEvolve comes along and finds a method using just 48.
Just 48. And look, I know dropping from 49 to 48 sounds tiny, right? Just one less multiplication.
Yeah, it does seem small on the surface.
But that single step is why this is such a profound result. So today, our mission is to really dig into why. Why is going from 49 to 48 such a big deal? What does it mean for computing, for AI, maybe even for how math itself gets discovered? We'll unpack how AlphaEvolve do it and, crucially, the real-world effects.
Okay, let's do that. Why is beating Strassen, even by one scalar multiplication, so significant? I mean, 49 was already way better than 64.
Absolutely. Strassen wasn't just faster, it was a theoretical earthquake. It proved you could multiply matrices with a time complexity, basically. How the runtime scales as matrices get bigger, that was better than the obvious n-cubed method. It broke a theoretical barrier.
So it showed there were potentially cleverer ways, fundamentally clever ways to do it.
Precisely. And that sparked this massive research effort, this decades-long quest to push down the theoretical exponent even further. The current best is around 2.37 something, incredibly complex algorithm.
And those theoretical ones are often not practical, but they push the boundary.
Exactly. But here's the key thing. All those advanced techniques, even the practical ones used in libraries today, they fundamentally rely on optimizing the small base cases. How fast can you multiply 2 by 2s, 3 by 3s, and especially 4 by 4s?
Ah, okay. So it's like the building blocks.
Totally. Think of building a huge Lego tower. The stability and ultimate height depend critically on how well those first few base layers are put together. Improving the 4x4 case is like strengthening the absolute foundation of all fast linear algebra algorithms.
Right. It ripples upwards.
It ripples upwards. And, for 56 years, the general feeling in the math and computer science community was kind of like, well, maybe 49 is the optimal number for 4x4 in the general case. It felt settled.
A reasonable assumption after so long.
Yeah, so AlphaEvolve finding 48, it's a real shock to the system. A powerful reminder that, even in areas we think we understand really well, there might be surprises lurking. Don't get complacent.
Okay, I'm getting it.
Yeah.
But maybe some analogies would help really nail this down, make it more concrete.
Sure, yeah. Let's try the cookie dough analogy again. Imagine you have two doughs, say, chocolate chip and peanut butter, and each has like 16 different variations or flavors.
Right.
The basic multiplication, the 64 operations, that's like baking every single possible flavor pairing. Chocolate chip variant 1 with peanut butter variant 1, then variant 2, and so on. 64 distinct batches.
Right.
Strassen's 49 operation method was like finding a clever way to premix ingredients or share steps, so you only needed 49 distinct prep routines to get all 64 final cookie combinations.
Clever shortcut.
Exactly. Now, AlphaEvolve, it found an even more ingenious prep routine. Needs only 48 distinct steps to produce the exact same set of 64 delicious cookie combinations. One less step, same outcome.
Less work, same cookies. I like that. Another one.
Okay, how about weaving? Imagine a tapestry. Cloth A has threads going horizontally, cloth B has threads vertically. Basic matrix multiplication is like every single horizontal thread crossing over every single vertical thread. 64 crossings for our 4x4 example.
Okay, grid of crossings.
Strasson's algorithm was like realizing you could design the loom or the waving pattern differently to skip some crossings that were, in a sense, redundant for the final pattern. Get the same tapestry with only 49 essential crossings.
More efficient weaving.
Right. And AlphaEvolve found a way to trim one more crossing, just one. On a tiny sample, maybe you don't notice. But if you're weaving a massive, complex image, like computations involving huge matrices, saving that one crossing, repeated millions or billions of times, that adds up to significant savings in time and effort.
Wow. Okay, yeah, those really clarify the cumulative effect. So this Darwinian Codemaster, AlphaEvolve, how does it actually work? It's not like it just knows math, right?
No, not like a person knows math. It's a pretty sophisticated system. It uses large language models specifically, from Google's Gemini family called Flash and Pro. But it uses them within this framework that mimics evolution. It's like running a giant computational evolution experiment.
Evolution for code. How does that actually proceed?
It's iterative, like natural selection. You start with a prompt. That includes the current best-known code for the problem, maybe Strasson's algorithm to start, plus maybe some random variations, some mutations, and crucially, very clear rules for scoring the output. How good is the code?
So the starting point and the success criteria.
Exactly. Then the Gemini models get to work. Flash is, well, flashy. It generates lots and lots of diverse code ideas quickly, like a brainstormer. Pro is more like the refiner. It takes ideas, maybe from Flash or the previous best, and produces fewer but generally higher quality options.
So explore widely, then focus.
Kind of, yeah. A mix of breadth and depth. Then comes the crucial step, automated fitness testing. The candidate code snippets are rigorously tested. Do they actually work? Do they give the right answer for matrix multiplication? How fast do they run? And critically for this problem, how many scalar multiplications do they use? It's all objective measurement.
No opinions, just data.
Just data. And based on that data, you get survival of the fittest. .code. The programs that perform best, correct, fast, fewest operations become the parents for the next generation. They feed back into the prompt, maybe get mutated again, and the cycle repeats. Prompt, generate, test, select, over and over, maybe thousands of times.
And over these cycles, new, unexpected solutions can emerge.
That's the idea, solutions that maybe no human would have stumbled upon because the search space is just too vast or the path too non-intuitive.
It's pretty mind-bending. Now, DeepMind also had AlphaTensor before this, right? How is AlphaEvolve different?
Yeah, AlphaTensor was a big deal too. It used reinforcement learning, kind of like AI learning chess or Go, to find faster matrix algorithms. But, and this is a key difference, AlphaTensor mainly worked modulo 2.
Modulo 2, what's that?
Think of it like math with only two numbers, 0 and 1, where 1 plus 1, 1 up. It's simpler, useful in some areas, but it's not the standard arithmetic we use for most scientific computing or AI.
Okay, so a more restricted kind of math.
Right. AlphaEvolve is a major step up because it works over general fields. That includes the real numbers, complex numbers, the kind of math that powers almost all real-world graphics, physics, AI. It's much more broadly applicable.
So AlphaEvolve is like the more versatile grown-up sibling.
That's a good way to put it. It overcame a key limitation of AlphaTensor and tackled the problem in the math battle domain that really matters for most applications.
Okay, so we've got the theory, the significance, how it works. But what about the real world? Has this one multiplication saving actually made a difference yet? Are there tangible benefits?
Oh, absolutely. The impact is already measurable. For instance, inside Google's own Gemini AI models, they used AlphaEvolve's discoveries to optimize the core kernels. These are the small bits of code that run over and over during training.
And the result?
A 23% speed increase in those specific kernels. And that contributed to about a 1% reduction in the total training time for the entire massive Gemini model. Now, 1% might not sound earth-shattering.
But for training models that cost millions and take weeks on huge clusters.
Exactly. That 1% is a huge saving in compute cost, energy, and development time. It makes building better AI faster and cheaper.
Okay, that's definitely tangible. What else?
There's also flash attention. It's a technique widely used to make AI models faster when they're actually running, doing inference, generating text, making predictions. AlphaEvolve's insights helped optimize the underlying math there, leading to a 32.5% speed up in those kernel computations within production systems.
So faster responses from chatbots, faster image generation, things users actually notice.
Potentially, yeah. It contributes to that overall efficiency. And it goes even deeper. Google's internal Borg system, which schedules jobs across their massive data centers, optimizations derived from AlphaEvolve freed up about 0.7% of their global compute capacity.
0.7% of Google's compute. That's like finding a whole extra data center's worth of power for free.
Pretty much. And it even reaches down to hardware design. AlphaEvolve suggested a small change in the Verilog code. That's the language used to design chips for an upcoming TPU, their specialized AI hardware. The suggestion allowed them to remove some redundant logic, making the chip potentially slightly more efficient. Human engineers reviewed it, agreed, and made the change.
Wow. So it's improving software, infrastructure management, and future hardware, all from shaving off one multiplication in a 4x4 matrix.
It really shows the power of optimizing fundamentals, doesn't it?
It absolutely does. Now, is AlphaEvolve just a matrix whiz, or can it do other things? You mentioned it's more general.
Yeah, that's maybe the most exciting part. It's not a one-trick pony. The team applied it to about 50 open problems across different fields: geometry, combinatorics, optimization, areas far removed from just matrix math.
Yeah, and how'd it do?
Pretty impressively. In about 3/4 of those problems, 75%, it matched the best solutions humans had found. But in roughly 20% of cases, it actually improved on the best-known human solution.
Found something better than humans had managed. Can you give an example?
Sure. There's a classic geometry problem called the kissing number problem. It asks, in a given dimension, how many identical spheres can you arrange so they all touch a central sphere of the same size without overlapping?
Okay, sounds tricky.
It is, especially in higher dimensions. In 11 dimensions, the best-known lower bound, the minimum number people knew how to fit, was 592 spheres. AlphaEvolve found a configuration that fits 593.
Whoa. It squeezed in an extra sphere in 11-dimensional space.
Found a way, yeah. It shows the system can explore these incredibly complex high-dimensional search spaces and find non-obvious improvements.
So what's the common thread? What makes a problem suitable for AlphaEvolve?
The key thing is having a clear, objective way to score a solution, a fitness function or objective metric. If you can tell the system precisely how good any given attempt is numerically, then AlphaEvolve can potentially work its magic.
So logistics, route planning.
Yep. Chip layout, maybe certain cryptography problems, protein folding. Anywhere you're searching for an optimal configuration or structure, and you can define what optimal means with a score.
This sounds like a seriously powerful tool. If someone listening is, say, a researcher, can they get access to this? How do they learn more?
DeepMind has actually opened up an early access waitlist. Researchers can apply to use AlphaEvolve for their problems.
How does that work? What do you need to provide?
From the descriptions, you basically need to define your problem clearly. That involves providing some code, probably in Python, that can run a potential solution, and crucially, an evaluator function that takes a solution and returns that objective score. How good is it?
So you package up your problem in the scoring rules.
Exactly.
Yeah.
Then you submit it to their system, and it runs the evolutionary search. It's not quite point and click for everyone yet, but it's moving towards accessibility for the research community.
And for understanding the 48 multiplication result itself, the nitty-gritty.
They've been quite open. There's a detailed public PDF, a white paper that lays out the AlphaEvolve architecture, the safety measures, and importantly, the full mathematical description of the rank 48 tensor decomposition. That's the math behind the 48 multiplications.
So the recipe is public.
The recipe is public.
Yeah.
And even better, they released a public Colab notebook. That's like an interactive online coding environment. You can run the code in that notebook to actually generate the mathematical factors for the 48 multiplication algorithm and verify they work.
That's great for reproducibility and understanding. Any advice for someone thinking of applying AlphaEvolve?
Yeah, the DeepMind team stresses this. Have a really good, clear, objective scoring function. AlphaEvolve needs that precise feedback loop. If your measure of success is fuzzy, the evolution won't be effective. Garbage in, garbage out applies here too.
Makes sense. Now, you mentioned the PDF offers more than just the 48 number. What other interesting stuff is in there?
Oh yeah, the PDF is great for comparing AlphaEvolve to its predecessor, FunSearch. They have this useful table showing the leaps. FunSearch could only really evolve a single function, maybe 10, 20 lines of code. AlphaEvolve works on entire code files, hundreds of lines.
That's a massive jump in scope.
Huge. FunSearch was basically Python only. AlphaEvolve can handle pretty much any language. The compute budget for evaluating solutions went from like 20 minutes on one machine to potentially hours on big clusters or accelerators.
Allowing much deeper searches.
Exactly. And how it uses the LLMs is different too. FunSearch used lots of small, quick LLM calls. AlphaEvolve uses fewer, but much higher quality interactions with the big Gemini models, feeding them richer context, not just past solutions, but feedback, metadata about the search.
More sophisticated guidance for the AI.
Right. And finally, AlphaEvolve can handle multi-objective optimization balancing, say speed and memory usage, whereas FunSearch was mostly psychometric. It's just a much more powerful and flexible system across the board.
It really sounds like a generational leap over FunSearch. And the PDF reinforces how that one multiplication saving cascades, right?
Absolutely. It draws that direct line to things like the 23% speedup in the Palace GMM kernel used by JAX and that 1% reduction in Gemini training time. Small base case improvement, big overall impact. But the PDF also hints at other cool things, maybe slightly understated.
Oh, like what?
Well, one is the portability of the rank 48 algorithm itself. The math works across different fields, real numbers, complex numbers, finite fields. It's quite general.
Ah, so it's not just a trick for standard computer arithmetic.
Exactly. Another neat detail, the changes AlphaEvolve suggests are presented as simple search replace diffs, just like a programmer would see in a code review. That makes them surprisingly human-readable and checkable. That was apparently key for getting that hardware change approved for the TPU.
That's clever, making the AI output easy for humans to verify.
Yeah. And maybe the coolest understated bit is the meta-prompt evolution. AlphaEvolve actually refines its own instructions over time. It learns how to prompt the Gemini models more effectively to get better code suggestions. Disabling this self-improvement reportedly slows things down significantly.
Whoa, the AI is learning how to guide itself better. That's pretty meta. So for the keen listener, what's the DIY tour?
I'd say grab the PDF, find Chapter 3 for the 48 method details and Appendix A for the full formulas, then fire up the Colab notebook, run the verification steps, see it work. And if you're really ambitious, try coding up the core loops yourself in NumPy or PyTorch or C++ just to get a feel for it.
That's like a good pass for the technically curious. Stepping back again, what does all this mean for programmers for how we optimize software in the future?
Well, I think it's a pretty strong signal, right? The era where humans do all the deep, tricky optimization might be changing. AI like AlphaEvolve could become a standard tool, like a compiler, but one that suggests fundamental algorithmic improvements, not just low-level tweaks. A kind of co-developer.
So AI helping us find breakthroughs.
Potentially, yeah. It might make certain kinds of theoretical discovery more accessible. Maybe you don't need to be a Fields medalist to find a novel optimization if you have the right tools and can frame the problem well.
That could democratize research in a way.
It could, but it also means we need to be ready to question established benchmarks and limits. That 56-year record for 4x4 fell. What else that we assume is optimal might not be. I actually remember years ago in grad school reading Strassen's paper and, kind of as a joke, penciling .48 in the margin. Never thought it would actually happen.
Huh. That's fantastic. A little foreshadowing. Okay, bringing this deep dive towards a close, what's the central message we should take away from AlphaEvolve?
I think the core message is that AI is now capable of driving genuine fundamental advances in computational mathematics. AlphaEvolve isn't just theory, it's delivering real, measurable speed-ups and efficiencies today in critical areas like AI itself. And its success hints at the potential for AI to accelerate discovery across many scientific and engineering fields.
But it's important to frame it correctly, right? This isn't Skynet taking over math. It's a tool.
Exactly. The researchers are very clear on this. It's more like an incredibly powerful, tireless, and sometimes surprisingly creative lab partner. It explores avenues humans might miss.
And if it can optimize something as fundamental as matrix multiplication, what's next?
Well, you can imagine applying similar approaches to other core computational problems, maybe in climate modeling, finding more efficient ways to run complex simulations, or discovering new structures in cryptography. The potential seems vast.
So perhaps a final thought for our listeners. The next time you encounter a problem where someone says, oh, that's the fastest way, we've known that for years, maybe pause for a second.
Yeah, maybe add a little mental theory. Because systems like AlphaEvolve are out there, constantly searching that vast space of possibilities, looking for ways to chip away at those long-held assumptions. It really makes you wonder what established limits in your field might be the next to fall.